Okay, Assalamualaikum dan selamat sejahtera. So this is chapter 2, which is final state machine. Okay, so first of all, final state machine have two types or two model, which are Moore model, and then another one is Mealy model. So this is the Moore model. Okay, we go to topic of outline. First is the introduction, structure of FSM, and then this video is for Moore machine. So Moore machine, we will look into what is the state diagram, truth table, and also FSM circuit. Okay, so these three is actually the main thing that we will do in this FSM, specifically Moore machine and Mealy machine. Okay. So for introduction, counter is known as a simple FSM because it has a regular numeric count, sequence, and less function. As we already learned before this chapter, counter, a sequence counter, and sequence counter. So actually, that counter is also called as a simple FSM. Okay, and then the definition of FSM is a sequential logic with a fixed number of possible states and has multiple functions. Okay, so this is the main difference between uh, FSM and simple FSM. Okay, counter is a simple FSM because less function. Okay, and they have a regular numeric count sequence. But for FSM is a sequential logic and a fixed number of possible states and has multiple functions. Okay, concept of FSM, we can say that imagine a vending machine that dispenses several items. Okay, this is a vending machine. We can say that FSM has a set of input events. Okay, different type of coin. For example, we have 10 cents, 20 cents, 50 cents, 1 ringgit note, and 5 ringgit note. And then we have a set of output events we call as type of items. And a set of states is the number of states depends on the price of each item. And a function that maps state and input to output. So the item will be dispensed if the price match with the input coins or not. Okay, for example, one item for this vending machine, we have if we want to get this one item, the price is for example 30 cent, so we have to put 10 cent plus 20 cent or 20 cent first and then 10 cent, and you can get the output. Okay, so FSM is actually a concept that are used for logic circuit, firmware for a microcontroller, and many computers and microprocessor chips. Okay, the other application of FSM is like this: vending machine, elevator, car, aeroplane, robot, traffic light, video games, and many more. Okay, and then in a digital circuit, an FSM may be built using PLD or programmable logic device, or we can use PLC, programmable logic controller, and we also can be use logic gates and also flip-flops or relays. Okay, as I said before, models for representing FSM have two models. First is Moore model, and second is Mealy model. Okay, so this is the owner of the model. Okay, structure of FSM. Okay, a final estimation is an abstract description of digital hardware. In general, a final estimation can be split into three parts. Okay, they have for FSM, they have three main parts. Okay, first is transition logic block. Okay, the state memory block and output block, output logic block. Okay, so this is the structure of FSM. Okay, you can see that this is a clock. Okay, and this is the input signal. Okay, this is the next state, and this is the present state, and this is the output signal. So you can see that this is a Mealy model only, meaning that to differentiate between more model and milli model by using this connection. So meaning that milli model, the output from milli model is depends also from input signal. Compared to more model, the output is depends only on present state. Okay. Okay. You can also differentiate that two FSM model by using this figure. Okay, more machine and milli machine. Okay, more output depends on present state only, as I said before. And milli model, the output depends on present state and input. So this is the main difference between more model and milli model. Okay. Okay, as uh, uh, the basic truth table for this is the basic truth table for FSM. Okay, it's like the excitation table for counter. Okay, so we have present state, input, next state, output, and flip-flop input. Okay, so this flip-flop input is depend on uh, type of flip-flops. Okay, so for more machine, the output depends on a function of the present state only. Okay, so the present state only. Therefore, the output can change only on a clock edge. So the output is written inside the state. So this one is you can see from this state. Okay, so compared to counter state, so for FSM in state we have input and output. Okay, for more model, the input will located outside state. Okay, this is state, this is the output, this is the input, sorry, this is the input, and this is the output. Okay, so output is located inside the state for more model. Okay, and then the input is on the transition, this one. Okay, so this is the same the example of the more machine state diagram, and this is the truth table. Okay, you can see that this is they have two state, state A and state B. Okay, so state A represented by 0 and state B represented by 1. Okay, so this truth table is like this, present previously. Okay, so this is the present state Q naught, which is 0 and 1 because this is two state. So state A contain only one bit and state B also one bit, 0 and 1. Okay, we analyze this one. So for state A, input 0, the next state will be A. So state A, which is present state, when when we follow the input 0, this one, input 0, the next state is state A also. Okay, so the next state is 0, which is A. Okay, and then the output is 1. So we put 1 here. Okay, and then next is still state A. Okay, state A 0, input 1, so input 1 here, 1 here, so next state will be B. So present state 0, next state 1, next state will be 1, which is B. Okay, 0 is A, state 1 is state B. Okay, 1 represents the state B. Okay, the output will be 1 because this is the more model. Okay, so more model, the output depends on a function of present state only. So if your present state for this example is A, present state is 0, which is A, so the output will be 1. So whenever the present state is A, so the output will be 1. Okay, so in this case not 0. And then next is present state B. So B represented by 1. Okay, so for input 0, the next state is B. Input 0, next state is B. B is 1, represented by bit 1, and the output is 0. Then another one is state B, present state is B, or represented by bit 1, input 1. So none of these arrow have input 1 for state B. So we put don't care here. Okay, don't care for next state, and output also don't care. Okay, and then this one is the flip-flop inputs. For example, we use D flip-flop. So this one, we can put this as by referring the excitation table. It's like the counter. Okay, usually for D flip-flop, we can simply copy and paste from next state. If the next state is like this, 0, 1, 1x, so your D flip-flop input will be similar, 0, 1, 1x. Okay. And then after that, after complete the truth table, okay, we can use this one to make a K-map to simplify to generate the equation. So this is the K-map. First, we will draw the K-map for output, which is Y, and then another one is K-map for D flip-flop. Okay, K-map for Y and K-map for D flip-flop. Okay, this one, this D is D0, so this will be D0, D0. Okay, you put the complete the K-map, and then you get Y equal to Q naught bar, D equal to Q naught plus Y, I, sorry, D equal to Q naught plus I, or Q naught or I. So draw the, after complete and get the equation from K-map, so we can draw the circuit. Okay, due to this design only have one bit, okay, only have one bit, so we have to use one flip-flop only. Okay, so Y is equal to Q naught bar. So where is Q naught bar? So this is Q naught bar. So your output or Y is connected here. Okay, this is Y or output, and then D represent D0 actually. So this D0 or D naught is equal to Q naught or with input I. Okay, so this is the connection. And don't forget to draw the clock. Okay, next is example 1. Okay, by referring to figure 1, fill in the truth table below. Okay, so this example have 3 states, which is S0, S1, and S2. So this is the table. So due to 3 states, so your present state and next state will be 2B. Okay, so S0 represented by 0, 0, S1 represented by 0, 1, and S2 will be represented by 1, 0. Okay, so we complete this truth table. Okay, like this. So for state S0, we have 0, 0, S1, 0, 1, and S2, 1, 0. Okay, input 0, next state will be 0, 0. Input 1, next state will be 0, 1. Input 0, 0, 0. Input 1, 0, 1. Okay, for S1, input 0 is S0, 0, 0. Input 1, 1, 0. Okay, for S1, 0, 0, 0, and 1, 0. Same goes to S2, 0, 0, and 1, 0. 0, 0, and 1, 0. And for what input present state 1, 1 is don't care because doesn't have in this Sure.